Hey everyone, this is John Oden on the development team here at Boson Software, and welcome back to our continuing series entitled Subnetting Demystified. This is presentation number 6 in the series, and in this presentation we're going to take up the topic of why do we subnet. In the previous presentations we've learned some basics about the IPv4 addressing scheme. We've learned about binary math. We've learned about classful and classless networking. And now we're going to start getting into the heart of our subject matter. Why do we subnet? There are a number of reasons why subnetting is important, and I've listed the big 3 here. The first of which is to be able to use the IP address space efficiently. Now we'll talk about exactly what does that mean. Also, we're going to talk a little bit about something called hierarchical networks, and we'll also talk a little bit about address summarization in a later presentation. But if someone were to ask you why do you need to be able to do subnetting, these are 3 of the major reasons. And the most major of these 3 is this idea of using the address space efficiently. We're going to go through some examples of exactly what does that mean. I would probably informally add a 4th item to this list, and that's to be able to successfully answer exam questions. If you're working towards an IT certification, one of the many IT certifications out there, lots of them are going to require you to be able to solve subnetting problems as a part of taking the exam. So first of all, certainly you're going to learn the material so that you can put it into practice and use it. But if your goal is to achieve certifications, then you're going to need to be able to work through subnetting problems for that reason as well. So let's get into this first idea of using the IP address space efficiently, and let's find out what does that mean. We have seen this diagram before in one of our previous presentations, and I'd like for us to go back to it and kind of spend just a minute or two reviewing what we're seeing here. Recall that this diagram represents what could be a lab environment, or you could think about it as a business that has 3 locations that are connected together via a wide area network of some sort, such that we have location 1 over here on this side with its local area network with some computers connected off of the local area network side of this router. We've got location 2 up here with the same thing going on, as well as location 3 over here. Now, if you look at the diagram, you can see that I've written some IP addressing information up here. I've done it a little bit differently than I did in the presentation where you saw this before. Now that we've learned about slash notation or CIDR notation, I have written it in this way such that we can see that we've got the 192.168.10.0/24 network at location 1 on the local area network side of location 1. Location 2 up here at the top, we've got 192.168.20.0/24. And location 3 over here to the right, we've got 192.168.30.0/24. Now, given this information, how do we break down the IP addressing information that we see here in terms of the network portion and the host portion? Well, we've got 2 different ways that we can do that. First of all, the most explicit way is that now that we understand CIDR notation or slash notation, we know that this /24 means that the first 24 bits of this 32-bit number represent the network, so that we could just draw the dividing line right here between the network portion to the left of the line and the host portion to the right of the line. Let me do that also. That was for location 2 up here at the top. Let me go down and do the same thing for location 1 right here. There is the dividing line between the 3rd and the 4th octet. It's also a /24. And we have the same thing going on over here with location 3. The dividing line is right there. 24 bits over from the left, all of that represents network, and these last 8 bits represent host. So from that, we know that, again, these are 32-bit values. We know that the first 24 bits are network in each of the three locations, the local area network side of location 1, location 2, and location 3. They're all configured the same way. We have 24 bits for the network and 8 bits for the host. So how many host IP addresses does that allow us to have in those 8 bits? Well, we've seen that by remembering our powers of 2, we know that we can take 2 and raise it to the power which is equal to the number of host bits that we have, which in this case is 8. We know that 2 to the 8th power, what is that? That's going to be 256 individual values from 0 all the way up to 255 in this last octet. But you remember, we've got to subtract those 2 special cases. We've got one special case where all of the bits are 0, which represents the network number, which incidentally is this 192.168.20.0. That is the network number, and that is one of those special cases. The other special case is 192.168.20.255, which is the directed broadcast address for all of the hosts in this network. And that's the special case where all of the host bits are set to 1. So 2 to the 8th equals 256 possible values minus the 2 special cases equals 254 assignable IP addresses that we could apply to hosts, and hosts are user computer workstations, printers, wireless access points, servers, and on and on. So we know, as a matter of review now, that we could have 254 hosts in each of these locations, and that's all well and good. But let's say that these are smallish locations with maybe somewhere between 1 and 2 dozen devices that are going to be at each location. So we'll never need 254 IP addresses at location 2 or location 1 or location 3. We might need something like maybe 20 or 30 IP addresses at these locations. So using the addressing scheme that we have, do you see how inefficient that is, that we've used up an entire chunk of our IP address space here that could accommodate 254 hosts? We've allocated that to this one location that we know will never have more than 20 or 30 hosts in it. And the same thing for these other locations. All 3 of these locations, we will assume, because of our knowledge of the organization, that we would never have more than 20 or 30 host IP addresses at each of these locations. So there's no point to allocate IP address space that would give us 254 IP addresses when we only need 20 or 30. Now, furthermore, I'd like for you to consider the wide area network connections between each of these locations. Now, it's very clear to us that the local area network side of each of those locations is a network that's going to have hosts on it. But we also have to realize that the network link that connects location 1 with location 2, location 2 with location 3, and location 3 with location 1, these have to have hosts on them as well. And in this case, the hosts on these are the router interfaces that connect to each end of this point-to-point. Let's just say it is a wide area network. So we've got right here, I'm going to draw a circle around that. That's a network. I'm going to draw a circle around that one. That's another network. And then I'll draw a circle around this one. That's another network down here. So we've got these 3 little networks that will never have more than 2 hosts. And those 2 hosts are going to be the router interfaces at each end of the point-to-point link. So if we were to assign a /24 here, and another /24 over here, and a third /24 down here, that would be a tremendous waste of our IP address space, because we would be taking a chunk of our IP address space that could accommodate, again, 254 hosts, and we would be applying it to a network that would never need more than 2 hosts. So this is just an example, another example of the inefficiency of using classful networking, because with classful networking, we're limited to basically just 3 sizes of networks. We could have a /8, we could have a /16, or we could have a /24. And in many cases, when we're dealing with smaller locations and certainly with point-to-point networks, even a /24 is far too big for what we need. So how do we solve that problem? Well, one way that we could solve that problem is to take a single /24 and then chop it up into smaller pieces so that we wind up with each piece being the right size for the network to which we assign it. And that is subnetting. Subnetting is the process of taking a given portion of an IP address space and simply subdividing it into smaller subnetworks, so that in our example, and we'll go through this example a little bit later, what we're going to do is to take one of these /24s that we already have. We're going to take 192.168.10.0. We're going to take that single /24 and we're going to see how we could chop it up so that one /24 would be able to satisfy the need for this entire topology, rather than having to have one /24 here and another /24 here and another /24 here and three more /24s for each of these point-to-point links, which would be a ridiculous waste of IP addresses. We're going to take one single IP address and we're going to chop it up so that it can service all 6 networks that we see in this topology. Notice I said 6 networks. Well, how did we come up with 6 networks? I thought we just had 3 locations. Well, that's true. We do have just the 3 locations. We have location 1, and that's got a local area network. You've got location 2 that has a local area network behind the router. We have location 3 that has one local area network on the local area network side of router 3, just like all the other 2 locations. But we also have to consider the point-to-point networks that connect router 1 with router 2 with router 3, and then router 3 back to router 1. So that's 3 more networks represented by these little red lines with orange circles around them. So that's a total of 6 networks in this topology, and we're going to take one /24 and we're going to break it up by using subnetting so that from one /24 network we can satisfy our IP address requirements for the entire network topology. Okay, so let's explore how we might use subnetting to make a more efficient allocation of IP addresses in the network topology that we saw before. Now, the first step in any sort of design process is to gather the requirements. So here's what we have. We have been given the 192.168.10.0/24 network. That's the address space that we have to work with, and that's all we have to work with. Now, if we look at each of our locations, we can see that we have to be able to support a certain minimum number of hosts at each of these locations. We can see that location number 2 has the largest number of hosts required. We need to be able to support 50 hosts on the local area network at location 2. At location 1, we need to be able to support 25 hosts on the local area network at location 1. And then finally at location 3, it's our smallest location. We need to be able to support at least 10 hosts on the local area network of location 3. And finally, we can see that we are told to make efficient use of the IP address space for the WAN links. Now, what does that mean? Well, our WAN links, as we've said already, are point-to-point networks, each end of the link terminating at one of the other router interfaces. So, for example, the WAN link that connects location 1 to location 2 connects to this router interface here, and it connects to this other router interface over here. So how many hosts will there ever be on that network? 2, right? No more and no less. So we're going to need to have a network here that will support 2 hosts. Same thing here on the WAN link between R1 and R3, or between location 1 and location 3. So we need 2 hosts there. And then finally we need 2 hosts on the link between R2 and R3, or location 2 and location 3. So we need 2 hosts up here. So there are the requirements for the 6 networks that we need to accommodate out of this 192.168.10.0/24 address space. 50 hosts at location 2, 25 hosts at location 1, 10 hosts at location 3, and then 2 hosts for each of the 3 WAN links that tie all of the locations together. As we prepare to get deeper into subnetting, let me introduce a new term and a new concept here. For quite some time, we've been discussing this idea of network bits and host bits and the dividing line between the two. All of that's still valid. We still need to be able to understand that. But when we start talking about subnetworks, we need to introduce a third category of bits, and those are subnet bits. Now, where do subnet bits come from? We've only got 32 bits, right? And that does not change when we're doing subnetting. What changes is that we're going to borrow some of the bits from the host portion, and we're going to claim those as subnet bits. Now, we'll get into that just a little bit later, but before we do, let's go back to this set of requirements that we've been given and figure out how many host bits do we need. That's really where it begins. We've been told that we need to have 50 hosts here in location 2, 25 hosts at location 1, 10 hosts at location 3, and 2 hosts at each of those 3 wide area network links. Well, what does that mean in terms of host bits? How many host bits do we need for each of those? So let's break it down. What we need to determine, we need to refer back to our powers of 2. So I'm going to take 2 here. And for each of these networks that we're going to allocate, we need to raise 2 to some number of power, to some power, to represent how many bits that we're going to need for host addressing. So in this case, let's say we took 2 to the 3rd power. What is that? Well, that's 8, and that's clearly not enough. 2 to the 4th power, that's 16. That's still not enough. 2 to the 5th, that's 32 hosts. Still not enough. 2 to the 6th. Well, now we're getting somewhere because 2 to the 6th power gives us 64 possible values. So 64 minus those 2 special cases would be 62 usable host addresses if we require or if we claim 6 bits for the host portion of our networking scheme here. So 2 to the 6th, that's 64, minus the 2 special cases, that gives us 62, and that will work for location 2. 62, is that too many? Well, yeah, it is. But if we were to use only 5 bits, 2 to the 5th is 32, and that's not enough. So you have to make a little compromise here. You got to have enough, and in some cases you're going to have a little bit more than enough, and it's never a bad idea to have some extra IP addresses available in case more hosts are added in the future. So for location 2, we need 6 bits for the host, giving us 62 usable host addresses at location 2. So how about location 1? Well, we'll go through the same routine. What if we were to take 2 to the 4th? Go ahead and write 2 up here. And if we were to raise 2 to the 4th power, meaning that we were claiming 4 host bits for this network, 2 to the 4th is 16 possible values, and that's not enough. We're told that we need 25. So what if we take 2 to the 5th? Well, 2 to the 5th is 32. Minus the 2 special cases gives us 30 usable host addresses. We need 25. That gives us a few extra, so that's perfect. 5 bits it is. So 2 to the 5th, that's 32. Minus 2 gives us 30 usable addresses with 5 host bits in location 1. How about over here at location 3, where we need 10 hosts? Once again, the same routine. We're going to take 2 and raise it to some number, depending on how many bits we decide to use. So if we take 2 and raise it to the 3rd power, assuming that we're going to maybe grab 3 bits for the host, 2 to the 3rd, what is that? That is 8 values, and we need 10 hosts, so that's not going to be enough. So what if we take 2 and raise it to the 4th power? What value does that give us? Well, that gives us 16 possible values minus those 2 special cases that we always have to consider where all of the hosts are 0 or all of the hosts are 1, so we subtract 2 from that. And with 4 bits for our host portion here, then that will give us 16 minus 2 or 14 usable host addresses. We need 10, so that's just perfect. So what about these wide area network links where we need some very small networks that will accommodate 2 hosts each? How do we do that? Well, we do it exactly the same way. I'm going to take 2 and write it up here. And what power could we raise 2 to to get the two host addresses that we need for each of these point-to-point links. Well, this is kind of an interesting case, and it works just exactly like the rest. If we raise 2 to the third power, we get 8 possible values. That's way too many. If we take 2 and raise it to the second power, and that indicates that we're going to be using 2 bits for the host portion with these networks. So 2 to the second power is going to be equal to 4, and we have to subtract those 2 special cases, and that gives us the 2 host addresses that we need. So as we go through the values with 2 host bits with 4 possible values, the first value would be 0, which is our network ID. Then the first host would be .1, the next host would be .2, and after that would be .3, which is the broadcast, and then .4 would be the next network. We'll get into more of that later. I realize I jumped ahead there just a little bit, but that is the way that we will start counting out and breaking these down when we start to explore exactly what are the network numbers and what are the actual host numbers that will be configured on these devices a little bit later. So we've seen how subnetting can help us take care of this first item, which is to use our IP address space more effectively and efficiently without wasting IP addresses. All 3 of these items are somewhat interrelated, but let me take just a couple of minutes to at least give you a high-level overview of what is this thing that we call hierarchical networking and what is address summarization. Now we'll get more into that a little bit later on, but at least at this point I want to introduce these ideas and show you a little bit about what they mean. As you can see, our organization has grown a little bit. Where we started out with these 3 locations in our previous topology, and we numbered them 192.168.10.0, and we talked about how we were going to break down 192.168.10.0 into the 6 subnetworks that would be required to service the 3 local area networks and the wide area network connections. It looks like we have developed maybe an additional couple of regions. Maybe this was the central region. We've got eastern region and western region. Maybe these are business operations on different continents. Use your imagination. It doesn't matter. But the point is we've picked up this original topology and we've replicated it in 3 different geographically distant places. And notice as we did so, we just picked up the next Class C network block, 192.168.20.0 for this region, and we picked up 192.168.30.0/24 for this region. And just as we broke those down for the first region to service the 6 subnetworks that we had, let's assume that we've done the same thing for these 2 new regions that we've now brought online. So now that our organization has gone nationwide or maybe even worldwide, we've established a corporate headquarters with connectivity out to each of these regions. And you can see that the corporate headquarters network, we have used the private Class B block 172.16.0.0/16 to address the networks at our headquarters location. And let's further assume that our corporate headquarters network is fairly complex, and even though I've not drawn in the detail here, there could be dozens of subnetworks within the corporate headquarters. Maybe it's a large campus deployment with a data center. And let's assume we've got some additional network connectivity going off to the side over here. It doesn't really matter what it is or where it is. Perhaps it's a manufacturing facility or a partner facility. Doesn't matter, just some separate piece of network connectivity branching off from the headquarters network. So given this more complex topology, let's talk about what is hierarchical networking. And we have done hierarchical networking here. And this is simply the idea of taking a larger block of the address space and breaking it down to service the needs of the various networks contained within. And we started doing that back when we built out our first location earlier in this presentation. So an important characteristic of this idea of hierarchical networks is that we start with larger pieces of the address space and we start breaking it down and breaking it down and breaking it down until we get smaller pieces that fit the need of the network to which it ultimately will be assigned. Another important characteristic is that these network blocks need to be contiguous. In other words, we should be sure that anything 192.168.10.0 is contained in this location. Same thing for 192.168.20.0 here and 30.0 here, 172.16.00 up here at corporate headquarters. And that is to say, we don't want to have a piece of 192.168.10.0 here and then another piece of it over here in this location, and we don't want to find pieces of 172.16.0.0 down here in this location. So hierarchical networking means that we design our IP addressing scheme in a top-down, contiguous manner, very much like an organization chart. So this is an example of an hierarchical IP addressing plan. So to the last of those 3 points that I listed on the slide entitled Why Do We Subnet is this idea of address summarization. So to understand address summarization, we need to know a little bit about how IP routing works. You'll recall back from our earliest presentation, or one of our earliest presentations, that this idea of IP routing is the way that layer 3 devices, and layer 3 devices typically are routers, they could be layer 3 switches, how they make path determination decisions to find a way to get from one part of a network to a distant network somewhere else in the topology. In order to do that, they maintain a data structure called an IP routing table that's basically a list of all of the networks that that device is connected to and all of the networks that it has learned about from a dynamic routing protocol such as OSPF or EIGRP, or static routes that are manually configured by the network administrator. So if we take this first location and think about router 1, router 2, and router 3, router 1 is going to need to know about all of the networks that router 2 is connected to. Router 1 is also going to need to know about all of the networks that router 3 is connected to, and the same thing is true for router 2 and router 3 about router 1. So each router needs to know about all the networks that its neighbors can reach. And it stores this information in the IP routing table. Perhaps this is something that you've learned already, and it's a little bit of a review. Wanted to make sure we're all on the same page with that. So the idea of route summarization is this. And here's the scenario. Let's say that we've got one of these devices over here needs to send traffic from the 30 network, the 192.168.30 network for this region way over here in the right, and it needs to send traffic over into 192.168.10.0 somewhere. So in order to be able to do that, do the routers over here in this region need to carry in their IP routing tables individual routes to every network over here in this region? Actually, they don't, right? Because the devices over here in this region, they don't care about all the little subnets into which 192.168.10.0 is broken down here in this region. All that the routers in this region need to know is to reach 192.168.10.0, and anything that is a component of that, just send it this way. So the routers that sit on the edge of these networks, they don't announce all of their subnetworks to their neighbors in the routing domain. They would announce only a summary. So at the edge of this network, we only announce 192.168.10.0 instead of all 6 subnets that we've divided 192.168.10.0 into. So from the perspective of this element of our network over here, and we said we don't care what it is. We don't care if it's maybe it's a partner network, or maybe it's a network at a manufacturing facility or somewhere. If a device in this network needs to send traffic to 192.168 anything, it doesn't need to know about all of the subnetworks that we've broken 192.168 into. All it needs to do is to send that traffic to the corporate headquarters, which is receiving only a summary of the routes contained within each region. And the corporate headquarters will then figure out, does that traffic need to go out either this link, or this link? And then only once we get to the edge devices in these regional networks do we start worrying about how to get to the individual little subnets within them. So that's the broad topic of address summarization. That gets a little bit, the details get a little bit beyond the scope of our presentation here, but I at least wanted to make the case for what it is and why having an hierarchical addressing scheme is necessary in order to be able to summarize effectively. And to be able to design an IP addressing scheme like this, you need to be familiar with the subnetting techniques that we're going to take up in our next presentation. So in this presentation, we've seen, at least conceptually, what is subnetting, and we've seen several reasons why we need to be able to work through subnetting problems. We need to be able to take a design specification for a topology, such as what you see here, and be able to take a portion of an address space and be able to break it down so that we have sufficient numbers of usable host addresses for each network that we have in the topology. We've also seen that by designing our networks in an hierarchical way, that facilitates this idea of route summarization, which we've also learned about. So that about wraps it up for this presentation. Be sure and tune back in to our next presentation, where we're going to take this topology and this specification that we've outlined here, and we're going to go through a mechanical how-to process of exactly how to derive the subnets that will accommodate the required numbers of hosts for each of the 6 networks in this topology. Thank you for viewing, and be sure and tune in to the next presentation in this series.